Hi Chem 240, it's Dr. Ricardo here. We are going to do the second video in chapter 13. We're going to start talking about the colligative properties. This is page 6 of the notes. Okay, so the colligative properties are an interesting group of properties. There are 4 of them that we're going to learn about later on, 4 of them that you really have to know and do math questions related to. And what are they in general? Well, what makes them different than most properties is they are properties of a liquid when you add a solute to the liquid. How does that solute change the properties of the liquid? So interestingly enough, it does not matter what solute you add to the liquid. As long as you're adding something to the liquid, it's going to have an effect on the liquid. So these properties are independent of what the actual particles are that are being dissolved in the liquid. So they're properties that depend on how much of the stuff you dissolve, but not on what it is. So the definition is properties that depend on the concentration of the solute molecules or ions in the solution, but not on the chemical identity of the solute. So we're going to be able to find constants, and the constants you're going to look up for the solvent, not the solute. So what are they? Vapor pressure lowering. When you add a solute to a solvent, the solute is going to lower the vapor pressure at which the solvent evaporates. So we know that there's a vapor pressure curve for water. That vapor pressure curve looks different for salt water. The salt in the water makes it harder for the water to evaporate. So vapor pressure is always going to be lowered by adding a non-volatile solute. Okay? Now that non-volatile solute can be ionic, like sodium chloride, or it can be molecular. For instance, sugar water has a lower vapor pressure than regular water. The sugar is non-volatile, so it's not going to evaporate, but you can decrease the amount of water that evaporates by adding a solute. Okay? Well, the consequence of lowering the vapor pressure is it's going to lower the boiling point. So boiling point is going to be affected by vapor pressure, and freezing point is also going to be changed. So what's going to happen to boiling point is going to be elevated. Once you start to dissolve stuff in the water, you're going to raise the boiling point, okay, of water or whatever solvent you're talking about. So the typical boiling point of salt water is not going to be 100 degrees Celsius. It's going to be something like 101 or 102 degrees Celsius, depending on how much salt you dissolve. Okay? Again, doesn't matter which salt, okay? All it has to do with is what the concentration of the particles are in solution. Okay, freezing point is going to be depressed. So if you want to melt ice, okay, so ice has a lower melting point when it has a dissolved solute in it. So if you had some salt water, you have to go to lower temperatures to try to freeze the salt water than you would be for fresh water. Okay? And lastly, there's a property called osmosis, which has to do with moving a solvent through a membrane. And we're going to learn the formula for osmosis. And osmosis is not a function of which kind of molecules are dissolved in the water on one side of the membrane versus the other, but just how much of each. So those colligative properties are going to come in a bit. Before we can do colligative properties, we need to learn some ways of expressing concentration beyond the normal everyday ways of expressing concentration. So the typical way of expressing concentration in life is percent, right? We're obsessed with percent. So when we talk about a 15% solution by mass, we're talking about 15 grams of whatever stuff we're interested in, okay, the active ingredient, divided by 100 grams for each 100 grams of total. So that's a way of expressing concentration. But in chemistry, there's going to be better ways of expressing concentration. So the first, and by far the most important one, the one that you're going to use throughout this course, you're going to use again in organic chemistry or whatever chemistry courses you take in life, is called molarity. Very important that you express molarity and use the symbol capital M, because in a few minutes I'm going to teach you another concentration unit called molality that uses a small m or a fancy script M. Okay, so we're going to use large capital M for molarity. Okay, so what is the molarity? The molarity is defined as the number of moles of solute that you have in your solution divided by the number of liters of solution. So notice the denominator is not of solvent, it's of solution. So this is the total, okay? So I need to know the total number of liters of solution that I have. So a lot of times I can't figure this out until after I'm done making up the solution. I don't know exactly how much water I need to put in because it's not per grams of water. I have to go ahead and make up the solution and keep on mixing the two together until I wind up with exactly the right volume of the solution. So we'll talk about that in a second. I'll do one for you. Okay, so here's an example. If I have a 0.2 molar solution of ethylene glycol, ethylene glycol is the active ingredient in antifreeze. Okay, in 2 liters of solution, the molality would be 0.2 moles divided by 2 liters would give you a 0.1 capital M solution of ethylene glycol. Okay, and the solvent is water. Okay. Here's some more units of concentration. Okay, so the one that I described earlier, the one we use in life a lot, is percent by mass. So whenever you do percent, you should tell us, are you measuring by mass, by volume, or the third way that you could measure is by number of molecules, which would be by moles. Okay, so we're going to have all three. Okay, but mostly we're going to do it by mass. And the way you can tell the world that you're doing percent by mass is you could write percent symbol M over M. And if you do that, you're telling the world you're talking about a 50% solution. M over M is 50 grams of the stuff that you're interested in divided by 100 grams total, right, of all of the materials that are present. So you do the mass divided by the mass. Say, sometimes you'll see mix and match. Well, you'll see somebody do mass in the numerator and volume in the denominator. We're not going to do that. Okay, you'll see like on shampoo and stuff, they'll do stupid stuff like that. But this makes the most sense. Is you want to do it either by mass, you want to do it by taking the volume of the material that you're interested in divided by the total volume, or the last way that you could do it is by the number of moles of the stuff that you're interested in divided by the number of moles of total. Okay, so those are the 3 ways. This is directly proportional to counting up the individual molecules, right? Because moles are proportional to molecules. Volume could be slightly different. This does not necessarily match up with this. These two things do match up for gases, and we'll talk about that, why that is later on. Okay, but by mass will almost always be different by volume. Okay. All right, so 4quickly, percent by mass is the mass of the solute divided by the mass of the whole solution. Here's an example. How would you prepare a 425 point gram sample of aqueous solution that contains 2.40% by mass of sodium acetate? So this is how much solution you want to make. This is the total, right? For some reason you need 425 of it. You have the percent. So what is it that you need to calculate? You need to calculate the part. How much sodium acetate do I have to put in? So I labeled everything. The percent by mass is 2.4. The mass of the whole solution is 425. We're always putting decimal points. This number has 3 significant digits. This number has 3 significant digits. Okay, so what did I do here? I substituted into the formula. The percent is the part over the total times 100. 2.4 is equal to the mass of the solute divided by 425 times 100. If I solve for the mass of the solute, this guy cross multiplies, comes up. This 100 goes underneath. The 100 is a perfect number. It's an exact number. We know percent is 100. So the number of significant digits is going to be 3 because the 2 data points are going to be 3. Multiply this by this, divide it by 100, you get 10.2. Notice, percent doesn't have units, 100 doesn't have units. So the only units is the units that were on the grams of the solution. Okay, notice if they gave you the grams of water here, right? You could not just plug that in here. This has to be the grams of the total. Okay, so sometimes it's going to take you a step or two to work your way back to figure out, okay, they gave me the mass of the solid and they gave me the mass of the solvent. So the mass of the solution, I have to add those two up to get the mass of the solution. Good? All right, last step. We figured out the mass of the solute is equal to 10.2. How much water would I need? Well, 425 was the mass of the whole solution. I have to subtract. It's not going to be a big difference, but does matter. You have to subtract the 10.2 grams of the solute to get the mass of the solvent. So how would I make this up? I get a beaker. I take my 10.2 grams of sodium acetate. I put on top of it 415 grams of water. Mix it all up. The whole thing would be 2.40% because 2.40 is the number that you would get if you take 10.2 divided by 425, right? Does that make sense? So there's a difference here, a substantial difference of about 10 grams between the mass of the water and the mass of the solution, right? This is the total mass of the whole solution after it's mixed up. Mix it up, you have a nice, clear, colorless solution. You look right through it because sodium acetate does not have color. How do you know something is totally dissolved? If it's clear, okay? Coca-Cola, when you look in the bottle, as long as the cap is on and it's not fizzing, yes, it's a brown color, but it's not cloudy. So all of the materials in the Coca-Cola, okay, the Coke syrup, everything, the colorant, all of those things are dissolved all the way down to the molecular level. Like, unlike milk, right? Milk is not, it's homogenized. They try to get the fat dissolved as best that they can, but it's not totally dissolved because fat doesn't dissolve in water. They just make smaller little droplets of fat that are sitting, that are quasi-dissolved or kind of temporarily mixed into the water, right? But if you wait a week or 2 or 3, right, if the milk didn't go bad, it would settle out, right? That's why cream, the fat rises to the top, okay? So we're talking about solutions, which should be at the end, after you mix this up, should be clear and colorless. Okay, second term, so we have molarity, we have percent by mass. Now we're gonna have a new one called molality. So be very careful. Molality, I'm gonna go way out of my way every time to make a super fancy script M so that you don't confuse it with capital M. Capital M is molarity, capital fancy script M is molality. They are not the same thing, okay? They're not the same thing. They're slightly different. Okay, what is the molality? Well, the molality of a solution, now for any solution, you can calculate this. You can give me the same solution, give me the details, and I could come up with the molarity, and I can come up with the molality. Sometimes they're very close, okay? Sometimes they're not. Depends on how concentrated the solution is, okay? The more dilute the solution is, the closer the two numbers are going to be to one another, okay? That's what's usually going to happen. So the molality is defined with the same exact numerator as molarity. It's the moles of the solute, the thing that you're interested in. If you want to know what the molality of sugar dissolved in water is, the numerator is going to be the moles of the sugar. Okay? This time, though, we're changing the unit and we're changing the substance. Don't use liters, use kilograms. So it's the mass of the solvent that goes in the denominator. The second subtlety is don't use the total mass of the solution. Use just the solvent. So this is a ratio of solute to solvent. Okay? So let's do this example and calculate the molality in this case. Okay? So easy example. 0.2 moles of ethylene glycol dissolved in 200 grams of water. So I don't have to wait this time to mix it up to bring it to the total. I know exactly how much water to add. I add 2,000 grams. Well, what's 2,000 grams? That's 2 kilograms. Now, I don't lose any accuracy. If this had a 2,000 at the end, this number would have 4 significant digits. So this number has 4 significant digits. Remember, all our numbers, everything I'm going to give you is always going to have a decimal point. Okay, so that's known very accurately. It's 2.000 kilograms of water. Okay, what's the numerator? 0.2, known just to 2 significant digits. That's why my answer is only known to 2 significant digits. 2 significant digits over 4 just gives me 2. And what's the unit when I have moles divided by kilograms of solvent, the water? Molality. Make a small m. Okay, another one. Mole fraction. Okay, so far we have percent, molarity, and molality. Okay, what's the third one? So we have percent, that's easy, you knew that already. Molarity, molality, and the last one is called mole fraction. Okay, X of A. What's A? The substance that you're interested in. So the mole fraction is the moles of the solute divided by the total moles of all of the different materials in the solution. So you have to go back and figure out how many moles of solvent you have, plus how many moles of each of the solutes you have. Everything that's in there counts in the denominator. So mole fraction is dimensionless. It's moles divided by moles. So it's just a ratio. It's not multiplied by 100, so it's not percent. So if I took 10 moles of substance A, and I divided it by, and I put it in with 10 moles of substance B, right? That would be, and I was interested in what is the mole fraction of substance A? Well, this numerator was 10. The denominator is 10 for substance A plus the other 10 for substance B, so that would be 20, right? So I'd have in the numerator 10 moles divided by 20 moles. The moles would cancel out, and my answer would be 0.5. You don't make it 50%. It's not multiplied by 100. It's not percent mole fraction. It's just mole fraction. It's just a ratio. So you're in mole fraction, the answers are going to be locked between 0 and 1, right? The maximum you could ever have is to have a totally pure substance of A. That would mean that the numerator and the denominator are the same. You'd get the number of moles of A divided by the number of moles of A, because it's pure, there's only A in there, and you'd get a big fat 1. So 1.0, right, is the maximum you can get. Well, what happens if you don't have any A in there? Then you'd have 0 in the numerator divided by whatever else you have, and it would go down to 0. So interestingly enough, mole fraction has a continuum, right? It's got to be someplace between, can't go on the other side of this, it's got to be someplace between 0 and 1. Those are the only answers you can get for mole fraction. Okay. These are pretty easy to do. When do we use mole fraction? A lot of times we use mole fraction with gases, because gases dissolve in one another completely, and we tend to think about them by volume or moles. Okay? Good. All right, next one. This is one of the harder questions that you're going to have to do in the course, okay? It involves a lot of steps, okay? So I'm going to go through one with you nice and slowly. You're certainly going to see this on the second exam, okay? So this is converting molality to molarity. I could also ask you to go the other way, from molarity to molality. So I would practice this both ways, okay? So here's an example. We'll go through it nice and slowly. An aqueous solution is 0.273 molal, small m, right, in KCl, okay? What is the molarity of this solution? Now, they have to give you the density of the solution. If you don't get the density, you can't do these questions. So given the density and the molality, how do you calculate the molarity? Right? So converting molality to molarity. We're going from script M to capital M. Okay? So let me get some paper. All right. So the first thing that you should do is pick apart what they gave you and see what information you have. Okay? So they gave you the molality. So break that up into what molality means. Here's the molality. Okay? So molality is defined as 0.273 moles of whatever substance you have, okay, for each 1,000 grams of water, because molality is moles for each kilogram. So I took the opportunity to switch right over to grams, right? 1 kilogram is 1,000 grams. So that's the information you have, and you want to convert this to the same numerator. It's just the denominator that's wrong. We need to get this from grams of water to liters of solution. So this 100 grams is going to be part of the answer, but it's not enough. That denominator is going to be a little bit bigger because I need the grams of the KCl that went into making up the solution. So how am I going to find that? Well, the first thing I'm going to need is figure out, right, pretty easy, is I'm going to take this number of moles and I'm going to figure out how many grams I had. Okay? So my KCl, look up potassium, look up chlorine, add them up, right? They're going to give you a total of 74.6 grams per mole. Let me see if I have a periodic table here to show you where that came from. So from our periodic table, just blow this up a little bit. Here's the K, 39.09. We can round that to 39.1, okay? And CL is 35.5. Look over here, a little hard to see. Make it a little bigger and a little clearer. Okay, hard for you guys to see, but you can look it up, 35.45. I'm going to round that up to 35.5. So just the two atomic masses, you get 74.6, right? This is the atomic mass for potassium. This is the atomic mass for chlorine. So that's where the 74.6 came from. Okay, so moles multiplied by molar mass gives you grams. All right, so we got the numerator. We have the total mass of the solution, right? 1,000 grams of water plus the 20.4 from the KCl gives me 1,020 grams of solution. Okay, next. Well, I don't use a denominator of grams of solution, right? Otherwise, I would just put this into kilograms and move it up here. I need to change this to liters. Well, that's why you need the density. If you want to know the volume that's equivalent to 1,020 grams of solution, this is the mass. The density was given to you. So what volume does that have? So I took my density equation, which you guys know, very easy, is the mass over the volume. So how do I get volume by itself? Bring that up, bring the D underneath. So just cross multiply and you get that. So the volume is the mass of something divided by the density. Both were given to you. Okay. This 1,020, you just calculate it. Make it a little smaller. Where did this come from? That came from the original question where I gave you the density. The density was given to you at 1.00 times 10 to the third grams per liter. So I gave it to you in grams per liter. Okay. And what happens is it's going to kick up to liters. If you got this in grams per milliliter, you'd get a volume in milliliters. You just have to change it to liters. But since I gave it to you already in grams per liter, just use it. So this came right from the question. Sorry, you can't see the decimal point. So this divided by this, grams cancel. Liters are in the denominator of the denominator, so they kick up to the numerator, right? If you're in the denominator of the denominator, division is the same thing as multiplication by the reciprocal. So I need to, instead of dividing by this, multiply by its reciprocal. Its reciprocal is L. So that gives me liters. Okay, last thing, the volume comes out to 1.009 liters. Go back and calculate the molarity. So this was a pretty dilute solution, so the two numbers are pretty close. The molarity is the same exact numerator, 0.273 moles of KCl. What is the volume of the whole solution? 1.09 liters of solution. So that's the definition of molarity. This divided by this, so you get 0.271 molar. Okay, well, what did we start with? We started with almost the same number, because this is a pretty dilute solution. The more dilute solution you have, the closer they're going to get. So this solution is 0.273 molal, and the same solution is 0.271 molar, only off by a little bit. Okay? Okay. So again, practice that. I can either give it to you that way, or same kind of question where I give you the molarity and the density and ask you for the molality. So same idea. What are you manipulating? The denominator. It's the denominator that has to get changed. The numerator is fine. Okay? So just go after that denominator. Start working on it. Change it. In the other case, you're going to get liters of solution. So the first thing is you're going to use the density to get the grams of solution. Then you're going to go back, use that numerator, figure out how many grams of solute you have, subtract that from the total grams, and then the grams of solvent, the water, goes in the denominator. So you work this problem backwards. Okay? You are responsible for it both ways. Okay? Good. All right. Here's another one. This one, sorry, make this a little smaller. In this question, we're practicing changing our units of concentration from one to another. Okay, so let's read the question. Calculate the percent mass over mass, molality, and mole fraction of methanol. Methanol is MEOH. Of a solution prepared by dissolving 10 grams of methanol in 100 grams of water. So I give you how we're going to make this up. Okay. I give you the amount of water they're using, and I give you the amount of methanol they're using. Never told you what the total volume of the solution is at the end. Okay. Because sometimes you would think that, okay, I could just add up these masses, which you can. The total mass of the solution is definitely going to be 110 grams. Mass is conserved. There's no chemical reaction going on here, right? And even if there was a chemical reaction, we have conservation of mass. So definitely at the end, how much material do I have after I make up the solution? 110 grams. But the volume I don't know. The methanol molecules and the water molecules have different intermolecular forces than methanol by itself and water by itself. These two molecules love each other. Methanol would rather be dissolved in water than it would be in methanol. Water would rather be hanging out with methanol than it would be with other water. So I'm telling you, if you took 100 milliliters of water and 10 milliliters of methanol and you mixed them together, first thing you noticed it heats up a little bit. Heats up a little bit because those molecules love each other. They get into a tighter liquid packing, right? Essentially, the interactions are better. So they get closer to each other. The volume would not be 100 plus 10, 100 milliliters and 10 milliliters. It would be something like 109 or even maybe 108, okay? Because there's a strong interaction. The adhesion, right, between the different molecules is stronger than the cohesion between molecules that are alike, okay? So these guys get along great, right? We have an interracial neighborhood finally, okay? So things get along. They like each other more than they like to be all by themselves. Okay, so one plus in the world. Here we go. So let's calculate this. So what is the percent M over M? Well, that's easy. This is just numerator divided by total, right? So that's how we do percent, right? You don't make a ratio, you put the total in the denominator. All right, I want to know the percent of methanol, they gave me that, 10 grams, divided by the total mass of the solution, 10 plus 100. So this comes out to 9.09% methanol by mass. Okay, grams and grams cancel. Why 3 significant figures? This guy's got 3, this guy's got 4, answer's got 3. Okay, what's the molality? Well, to get molality, I need to convert the numerator to moles. So methanol, here's the formula for methanol. Methanol looks like this. Pretty simple molecule, right? So that's CH4O. Okay, so you need to add up a carbon, which is worth 12, 4 hydrogens, each one is worth 1, and 1 oxygen. Okay, so I get 20, 32. So I get 32 flat. What did I use? I used 32 flat. Good. Okay, so if I want to get to moles, I divide by the molar mass. Grams cancel, and I get moles. So that's from Chem 1. Right? Moles in the numerator, moles of solute. Okay, what goes in the denominator? Kilograms of just the solvent. They told me I had 100 grams of water. All I have to do is convert that to kilograms. So 100 grams is 0.1 kilograms. That's it. This is not the solution. Molality is a ratio. This is just the water. Okay, take this, divide it by this, get your answer to 3 significant figures, because both these had 3 significant figures. Okay, mole fraction. To do this, I need to calculate the moles of each, right? Okay, so the moles of methanol we had from this part up here, so we don't have to redo that. 0.313 moles. We need to get the moles of water. Well, I have 100 grams of water. Water has a molar mass of 18. You remember that? Oxygen is 16. Each hydrogen is 1. So that gets you to 18. 100 grams divided by 18 grams per mole gives you 5.56 moles of water. Well, in mole fraction, I need the moles of the thing that I'm interested in the numerator and the total moles in the denominator. So the total moles of the only 2 things in the solution, the water and the methanol, comes out to 5.87. That's the denominator. It's the moles of methanol divided by the total moles, not just the moles of water, not just the 5.56. That would be a ratio. Okay, in terms of units, mole fraction has no units. Moles divided by moles cancel out, so you just get a number without a unit. I know it looks weird, okay? That's it. XMeOH, the mole fraction of methanol, is 0.0533. So by moles, it's 5.33% methanol, a little bit less than 95% water, okay? That's if you do it by moles. Moles is directly proportional to the number of molecules as well. Good? Okay, I'm going to stop there. So this is a shorter 33-minute video, and then start with the colligative properties on the next one. So the next one, I think we should be able to either finish or come pretty close to finishing chapter 13. But you probably need a little break after half an hour, and it's a nice natural place to stop. Okay, so the next one is going to be colligative properties.